So thank you again for having me here to the entire conference organizers. And today I'll be speaking about synchronous web apps and how we can approach web apps from a messaging architecture point of view. You know, as developers, one of our greatest and perfect dreams is to get our hands dirty with code. What I mean by saying is that as developers, nothing excites us than getting to work on a project with tons of integration patterns, right? Creating databases, entities, defining workflows, and if you have a ton of external APIs, you know what? Let us just get through it. You can't just wait to work on such a project. Sounds perfect, right? And I think that's a very relatable situation for all of us who are developers. And it's a dream come true as well. So we work on such projects and then we put our projects live. Fantastic. It's a moment of pride and joy when your project hits production and starts making money for the business. And there's no other joy like showcasing your own work. Again, something relatable. And then comes that first campaign that goes out as a mass email to how many people? Just about a few 100,000 people that the business has gained as the customer base. And then starts your rainy day. How? Because you notice sluggish front ends, or you get phone calls saying you have sluggish front ends. You notice that the backend services are not scaling quite well, or they are struggling to put up with the load. You might be taking payments on the side and that doesn't seem to work, or your payment processing gateway is hitting rate limiting territories. And at some point, you know what, the site just gives up, saying that, oh, I can't deal with this. I cannot deal with the spikes. Just do whatever you can. Now, this is something that we all have been there, done in the past. I have been there, done that myself. But there are other ways to face this reality more confidently upfront. And messaging is one such technology. And sorry, my slides are frozen. Why? What happened there? Okay, no. I am Purnima Nair. I'm a software engineer and solutions architect at Particular Software, where we build N-Service Bus and the entire service platform around N-Service Bus. I'm speaking to you from Berkshire in United Kingdom. And if you have any questions, reach out to me, DM me at Purnima Nair. I am as Purnima Nair on LinkedIn, X, and Blue Sky. So any questions, feel free to DM me and I'll try to answer you with as many answers, the best answers that I can. So in the next 35 minutes, we'll pick up some basics on asynchronous messaging and how we can use messaging as an architecture to have really high throughput, high performant, mission critical systems. And we'll see some code as well. When it comes to mission critical or high performance system, the first thing I like to talk about is the order processing system. Why? Because it's a very relatable workflow for everyone. It is the holy grail when it comes to building distributed systems and talking about distributed systems. And what is a typical workflow? We go to the website, put a few products into the basket, click checkout, put our details in, then fill in the credit card details, and then say place order. Boom, and that order goes into the backend system of the online shop, and then it gets processed. That's the happy day. That's not the rainy day. That's the sunny day that you can see, just like the day I have out here in UK. That's a perfect case scenario. Now go back and rewind to that campaign scenario. Where were you at that point when you had that rainy day? So we had a sluggish day. We started off with sluggish front ends. Sales are reported to be very low. Fine. You know what? We are on Azure. Let's just scale the front end. Auto scaling is what? 10 minutes max? Fine. We do that. Have we solved the problem? Not yet, because our backend services are struggling to cope up. It's still slow. Fine. We are going to auto scale our backend services. Now, there's a catch there. Legacy backends. Who has dealt with a backend system or API server hosted in an old server somewhere in the basement of a building? Been there, done that. There's an API which just couldn't be scaled. That's a catch in itself. Let's just not talk about it. But let us say that we have started scaling our backend services as well. And then at one point, we hit the wall, the database. So we have been moving the bottleneck from the front end to the backend services to the database, where it just goes boom. You know what? I cannot cope up with the amount of traffic that is hitting me, says the database. There's so much resources that you can throw at it, but what really happens is cascading failures. The database fails, it then goes and fails the backend services that we have scaled out, and that goes and fails the sluggish front end, which is also being scaled out horizontally, vertically, all way, but it then just blows up on the face of the user. We are not making money as a business. And that is the rainy day that I've been talking about. Yeah, so I've been there, done that myself years ago. I was working on a system, and when the mass email campaign went out to their very loyal customer base, we had like tons of people hitting the website, and we had a legacy API. And there was a point where I live monitored a system with my colleague over a phone call with a customer, and that went on for a couple of rounds. And that is where we start thinking about, did I use the right tool for the project? You know, could I have done this better? So what did I miss out? Did I miss a memo? And the memo that I missed out happens to be the fallacies of distributed computing. So what we have been speaking about so far is a distributed system where two or more computers speak to each other. So as developers, when we develop distributed systems, we take many, many things for granted. And those false assumptions have been coined together as the fallacies of distributed computing, the things which we fail to see upfront. This is a list of fallacies that was put together originally by Peter Deutsch. I will be leaving a link to all of this in my resources at the end, so keep on watching. But let us talk about these fallacies for a minute. We assume that the network is reliable. We assume that network will always be up and everything that we send will be received. But in reality, network can fail, information can get lost, and network could become congested, right? We assume that latency is zero. We assume that requests will complete instantly. But in reality, there is always a delay, millisecond, microseconds to even more in some cases. We assume that the bandwidth is infinite, but bandwidth is finite. There's a limit to the bandwidth. You can have slowdowns and bottlenecks. We just cannot send as much data as we want at any point. We assume that the network is always secure. We assume that, now my network is secure, there's no one coming to attack it. But we need to understand that in flight request, there's always a chance that someone could intercept it. We assume that topology doesn't change. We assume that servers, nodes, routes, they all are static and constant and they don't change. But in reality, machines crash, they restart, they get migrated, they scale up and down. So we cannot assume that there is no change. In fact, change is constant, and as developers, we need to embrace it. We assume that there's just a single administrator. But in reality, there is nothing called a centralized control these days. It's more about distributed teams. You could have multiple teams working on the same distributed system. And when that happens, if you don't have enough inter-team communication, inconsistencies and failures happen. But is there something called as enough inter-team communication? I don't think so. We assume that the transport cost is zero. Even if we have infinite bandwidth, the transport cost is not zero. There is a little bit of that extra that you pay at the end of every month with your Azure bill that comes around. That is what telling you is that transport cost is not zero. There's always cost associated, even with CPU performance and usage. And we assume that network is homogeneous. But is the network homogeneous? Is the behavior always uniform? Never, because no two systems or no two servers are alike. Let us go back to our order processing workflow and see what might the workflow be. So we have our website, which is pushing the orders, or when you hit that place order button, goes into a big service called the order processing service. The order processing service then might reach out to the sales service and say, hey, create this order for me. And the sales comes back with a response. Then the order processing goes and talks to the order payments. Sorry, the payments is hidden here. The payments and says, hey, build this for me. And then somehow it gives a response magically. And then it goes and talks to the customer status service to update the loyalty points. And then it might then give the response back to the order processing. And then the response goes back all the way back to the client. That is when the client gets to know, yeah, the order has gone through. Now, what you might have compare this with the policies that we just spoke about. What if one of the services is down? What if the network is congested and the data doesn't reach on time? There could be the chance of HTTP timeout exception, right? What if one of these services has been updated by a team and the other services just cannot cope up? There is the risk of that too. So what we have is a scenario of very tight coupling. Each service, like if you look at the order processing service, it needs to know that it needs to call the sales, it needs to call the order, it needs to call the order payment, and it needs to call the customer status. Why? Why can't just the order processing hand off and then just move on to do other things? That is what you want to do, right? Here, there's too many responsibilities on any service that is doing it. And you might think at this point that you can bring in Poly to keep doing the retries if there's failures happening, but that's not enough, because what about the data and the idempotency around it? Do you want to take the payment twice? No. The underlying problem here is what's known as temporal coupling. This is the tight coupling that I've been talking about. The idea that for two services to communicate to each other, they should be up and running at the same time. So if there's a sales service and the order processing both needs to be up and running, I need to get the response back after talking to B directly, and only then can I move on. So if B crashes, there is no request, there is no response, right? And at that point, A is completely blocked, A cannot do anything, and there's failure on the face of the user. And while that request has been sent to B, A is still waiting, doing nothing. Yeah, that is money lost probably during that time in compute power. There's also the request response pattern that we see here. I am not saying that this is a problem, but when it comes to high throughput, high performant scenarios, we cannot rely on request response because it follows the synchronous processing technique. Because HTTP by nature is synchronous, we cannot have async processing with request response. So this is also that something cannot really fit into this high throughput, high performance scenario, mission critical systems. So what we have built here is a house of cards, and not just a house of cards, but one that is sitting on top of Asian waves. Now, this is not about bashing HTTP APIs or gRPC, GraphQL, whatever, because they are all battle tested. They are there for a purpose. What I'm talking about is mission critical, high throughput, high performance systems where time is money, where you cannot have failures, and probably there an HTTP-based API is not something that you should be using. And how can we change this? How can we have better foundations? By introducing what is known as a message queue. So in reality, it is not as simple as this. There's a lot of thinking about the problem and the solution before you go into implementing this. But to have an introduction to messaging today, let us just assume that we have introduced a message queue in between. What is a message queue? Consider it like a database, but instead of rows, you have little messages. And what are messages? They are basically what you would have in your request, information. So with the message queue in place, A will actually send a message into the message queue. And at that point, the message gets stored into the message queue. A is not blocked at all. A can continue doing whatever else it needs to do. And B is on the other side of the message queue. B might be crashed at that point. B might be undergoing an update, or B might be online. But whenever B is ready to process things further, it takes the message from the message queue, processes it, and deletes it. So in a single shot, we have gotten rid of the temporal coupling, and note that there is no request response. Why? Because message queues or message brokers, they rely on protocols like AMQP, which by nature is asynchronous processing. So where do we start with this? I'm going to be focusing on the technical aspects of it. But if you want to head over to particular.net/blog, which I'll be sharing a link today, there's a lot of information about what goes into actually planning such a project. How can we migrate, or how can we even start greenfield projects? But today, in this 35 minutes, I just want to focus on the technical aspects of it. So the main thing to talk about, or the first main thing to talk about, is the message queue. There are a variety of options out there. It can be queues or brokers. Brokers are much more advanced in terms of functionality with routing and message filtering, message transformation. a talk for another day, but understand that there is message brokers and queues. So there's RabbitMQ, the open source. If you want something in the cloud, which is a more queue version, you have Amazon SQS. Then you have Azure Service Bus, which is in Azure cloud. And then you have ActiveMQ, ZeroMQ, IBMMQ to Google PubSub. Now, all this are infrastructure. This is extra infrastructure being brought into place. And then you also might be moving in from an HTTP to a messaging environment. So you might want to play around, have a look, gain some confidence about messaging in general. In such instances, we have seen database as queues, using SQL Server as queues. Why? Because such organizations who doesn't have enough confidence with messaging from the word go, they find it easier to have SQL Server, which they might be already using in the application, and use that as a queue. It's okay in that kind of a scenario to use it, but when you think about real high throughput scenarios, using database as a queue is probably not a good idea, because it's also adding load to your own database service. Now, we have our messaging queue in place. Suppose, say, for today, I'm using database as the queue because that is the easiest to set up. But say, if you are using RabbitMQ or SQS or Service Bus or even database as the queue, how would you go about talking to it? Would you use the native client library? Not really, because there are so many things that you need to ask yourself when you go down this path. What patterns do you need to support? Is it send and receive and publish subscribe? Which one do you need? Because with publish subscribe, you're going down the event-driven architecture route. What is your average message size? Do you need large message support? What about the complex routing that you might need in place? Do you want to write things yourself? No. How about the message delivery order and the delivery guarantees? Are you after at least once, at most once, or exactly once processing? What about data transactionality and the idempotency of data? Surely you don't want to take payment twice. What about the throughput? Do you want managed service or self-hosted service? Are you after cloud-native solutions? To what local dev support you need? All these are things that you need to ask yourself. And on top of that, you need to be also thinking about a variety of patterns that I'm just going to talk to you about. Message routing, workflow, transactions, claim check pattern, serialization, retries, monitoring and alerting, because it's a distributed system. All in all, you might end up writing all these patterns that you see on the screen. So would you want to do that yourself, or would you want to do it a different way? That is where messaging middlewares or messaging libraries come into play. There are many options which I'll be talking about, but I'm going to use the analogy of a car here. Suppose you want to have a new car with all the latest features out there. Would you go buy a car for yourself and use the amenities that it provides you with? Or decide, this sounds fun, let me actually build a car. Trust me, there are people who build a car. But then you have to think about the roadworthiness of it. You have to consider the paperwork that goes behind it. Do you really want to be doing it? Of course, there is the learning. But then one of the key learnings at the end of it would be, I don't want to do it ever again. I don't want to be servicing this car. It is going to sit as a car which is not going to be used on my driveway. I built that car. That is it. I don't want to be servicing it. So my point being, do not reinvent the wheel, use one of these libraries. And Service Bus, Mass Transit, Writer, Rebus, Wolverine, all of these are messaging libraries. They all come with patterns that I just spoke about that has been built in. You can make use of those amenities yourself. So this helps you focus on the business code. In today's example, I'm going to be using Service Bus because that is what I am used to. But regardless of that, feel free to use any of this, because all the code that I show you, it is just the APIs that keep changing. The patterns are the same regardless of the library you use. So just putting it out there, do not reinvent the wheel, because what you might end up writing is a cheaper version of one of these libraries that is going to cost you a fortune in the long run servicing and maintaining it. Save yourself from the headache, because a distributed system is no mean feat. So time for some code now. So what we will discuss are these main points: endpoints, commands and point-to-point communication, events, publish and subscribe. We will see if we can extend our system if time permits, and we'll also talk about recoverabilities and retries. So let's go to Rider. What I have here is a solution with 4 projects. I have unloaded something. Let us bring that into picture when the time is ready. So the client UI is basically the website, which is the web front end, ASP.NET Core MVC application, nothing too fancy about it. And I've got 2 services, which is the sales endpoint and the billing endpoint. So in reality, I might be hosting these as Windows services, the billing and the sales endpoints as Windows services, or even as like an Azure web job. The client UI, that is a website that could be hosted anywhere or even on Azure. So as I said, I'm using N-Service Bus because that is what I am familiar with, but feel free to use Mass Transit or Wolverine or Rebus because the patterns just keep repeating. It's just the semantics and the APIs, the names of the APIs and the methods that keep changing. So in my controllers, I have the home controller. There's a place order button. So if I just run this demo and show you what the web front end looks like, it is very simple and basic for this 35-minute session again. So I have this big button which places an order, and it tells me that an order has been placed. So when that place order button is clicked, what happens is it goes and invokes this action method for me. So in here, I create a new order ID, and then I instantiate something of the type place order, and I am sending that object that I've just created using something called message session. So what is actually happening? So message session is like an interface in N-Service Bus that helps me do basic operations on the message, like sending a message or publishing or receiving a message. And I am using that to send something. Now, what is that something that I'm sending? So if we look at the place order class, it's a plain old CLR object, which inherits from I command. And this is what I'm sending. In reality, it will be your entire request, which contains all the details of the products and everything. That's one way of doing it. But inheriting from I command is telling the system, that is, it's telling an N-Service Bus that, hey, this is a message. This needs to be treated like a command. Now, in comes the concept of the 2 different types of message here. This is a command. A command is an instruction. So it is a very valuable method. And me as a sender, I expect someone to take action upon it. So if I expect someone to take action upon it and it is a high value thing, I need to make sure that I know at least who is going to deal with it. So that also can be configured. But as a sender, I don't need to know whether that receiving party or whoever is going to deal with my instruction is up and running or down or whatever. I just need to know that there is this someone who I need to send the instruction to, who is going to do the work for me at some point. So using the message session, I'm sending that command, and how that sending is controlled in a centralized manner is from the program.cs. So here I have this API called route to endpoint, where I say the type of place order classes or the objects of type place order, the destination would be the sales for it, the sales endpoint or the sales queue. So as you can see, there is a website and it is talking directly just to the queue, not the sales service. It's the sales queue that it is talking to. So it centralizes all the connection for me. And this is now also an endpoint because that is how we treat things in N-Service Bus. And endpoint means it's a service that can send or receive messages. And of course, there is the configuration for the SQL transport, which I'm using today, and a little bit of N-Service Bus endpoint configuration. So that is the client UI, which sends the message or sends the command. Now, let us go and visit the sales service. So the sales service is where the place order instruction is received. So it needs to process that command. And for that, there is a class which says that, hey, I am here to catch all the commands that you send of the type place order. Let me deal with it. So in the place order handler, we have a class that inherits from iHandle messages of type T. So marking a class inheriting from iHandle messages of the type place order is shouting out loud to the system that I am here to handle all the commands or all the messages of the type place order. And inside my handler, there's a handle method where I can get the message as well as the context. So if you think about HTTP context, The iMessage handler context is something like that. It gives me access to the context because this is a service that has been invoked by a message. With HTTP APIs, you are invoking using HTTP request. Here, it is invoked using a message. So in here, I can then do some business logic, that is processing the order or saving it to the database in this instance. And then we have some interesting things happening. If you see here, there is another object called order placed being instantiated. And I'm using the context API, the publish API in the context to publish it. Here, I'm not sending, I am publishing it. So what is the difference? So this is an event. Event is like letting the world know that something has happened. While command is an instruction that says, do this, event is like something happened. I have done it. So the sales endpoint or the sales service is saying that, yeah, I have saved the order to the database. My job is done. I am just letting others know that I have done my job so that others can pick up on what is left to do. So as you can see here, there's just one responsibility residing on the sales service, which is creating that order in the database. So another thing to note here is that the order placed event is again very lightweight. In reality, it might be different, but the order placed inherits from I event, which lets the system know that this is an event. Now, if you look at the semantics of a command and event, the event semantic is a noun plus a verb in past tense. And for command is like a verb in present tense plus a noun. So that this way you can easily make out which is a command, which is an event without even going to the without even going inside the class and peeking into the class. So something like a best practice. So now we have published the event. And if you look at program.cs, I'm not talking to anyone, right? Because that is because this is an event. I just need to let the world know whether someone will listen to me, how many listeners will be there. I don't care. I just need to let the world know. It is like me talking to you. It's like a broadcast. There could be one or many listeners, and those listeners are called subscribers. And this is the basic of event-driven architecture. What we are doing as a pattern is publish, subscribe, and this is the basics of the event-driven architecture. And the beauty with event-driven architecture is that we get the space to extend the system easily because we can bring in more subscribers without affecting the system as a whole. Now, how do we handle this order placed event? That is getting done in the billing endpoint or the billing service. Here we have a handler, again, which inherits from iHandle messages of type T, which is order placed. In the handle method, I can again do some business logic. And then at the end, I might send another command or publish another event. That is also possible. Now let us see the demo in action.
Yeah, that's what there's spun up that new box, the one that is
so let me bring up the report for the run window. So I have the client UI here. I'm going to place a few orders. Just let us start with one to begin with. That is CFB4 is the starting. If I look at the sales, it has received the place order instruction. So if I look at the client UI to begin with, I'm sending the command for the order ID CFB4. The sales receives it and then publishes the event for the order ID. And in the billing, I have now received the order placed and I can move on and do other things. Now, we spoke about extending the system, right? So I have another service that I have just hidden here. I'm going to load the project and then I'm going to run this as well. So right now it is not running at all. I'm just going to run this. Again, this is a very simple handler which handles the order placed. And if I run this now, that should also run. Give me a minute. I think this is up and running now. If I go and place a few other orders, I should see that the shipping or endpoint should receive some of the messages as well from the past. So we have extended our system without impacting the system as a whole. Now, what if one of the endpoints is down? It has a bug. What happens behind the scenes? That is when the recoverability and the retries come in. So let us go and introduce a bug into our sales endpoint by just throwing an exception. So we just stop this and then rerun it all.
that.
So the sales endpoint is completely failing at the moment because I have introduced a bug, but that doesn't prevent the UI from working. I have placed a few orders now, and the client UI must have sent a few messages. But when it comes to sales, it keeps on failing. So now what happens is, in the sales, I've got some recoverability in place. This is something that you would add to every endpoint. And with the recoverability, it says that, hey, when you have an error, retry it. And when the first retry fails, then back off exponentially. 2 seconds, 4 seconds, and so on, till to the point you cannot do it anymore. And then what you do is you don't sit and do anything. You move that message into another queue called as the error queue. And that is what is going on here. I think it retries for like 3 times before it completely backs off and moves the message into the queue. So if you look here, there should be some messages in the monitoring area, which I'm just going to show to you right now.
Yeah.
Let me bring that up here. I should see a few failed messages. So if you look here, there is a message that has failed with the message body DF5CE, and that is indeed one of the messages that was sent by our client UI here. So at this point, sales is failing, but the client UI is up and running. So now let us simulate the scenario where we have gone and fixed the bug. Yeah. So here we are in the placeholder handler again. We have fixed the bug and we are running the app again. And now what I can do is when things are up and running, I can go back to the monitoring area and then start retrying my messages, the failed messages. So I can go into here.
There's definitely not in the console.
Here, in Service Pulse, and I can see failed messages. I can go into one and I say retry this message. Yes, I want to retry this message, so it is getting retried. Now if I go into sales, I should see that it is going to try and pick up the message that just failed. So let us see. Come on.
Because we don't.
It is retrying.
I can send you. I can export this wherever they are, but I mean, we don't get tickets for these. I mean, security is not bothered.
There you go. So the message with the message body BF5CE that has been retried, and the order has been order placed event has been published, and then the billing can receive it and the shipping can receive it. So the idea is that you can extend the system, and even if there are failures, the request is safely and durably stored somewhere, be it the error queue, so that you can bring things back up and retry it. So you're not losing any message. You are building that defense in place so that nothing is lost. Similarly, we can select all and retry, and it should all go through without overwhelming the system, or it should at least get processed one by one. So we should see that in action any minute. So I'm just going to move on and we can come back to it and visit the logs later. So we discussed all of this: endpoints, commands, and point-to-point communication, events in publish and subscribe. We saw about how you can extend your system without impacting the rest of the system. We saw about recoverability and retries. So we have moved on from that very monolithic architecture to something like this. So you have the client UI, which publishes, it sends a command saying place order to the sales endpoint. The sales endpoint then publishes an event called order placed, which is consumed by both billing and shipping. And here it gets interesting because the billing can then produce further events to say, I have billed the order, at which point the shipping can chip in and say, you have placed the order is confirmed, you have billed the order. I might also want to wait for the stock service to come back and tell me that there is enough stock so that I can start the shipping. So that is a very complicated thing happening behind the scenes, and that is yet another integration pattern called the Saga pattern, which you might want to invest and investigate, and that is used for having or creating workflows. Further, the billing might published the same order billed event that the billing published. It might be used by the email service to pick up the fact that a confirmation email needs to go out to the customer. And finally, the order billed that could be picked up by the customer loyalty service to say that, yeah, I have updated the customer loyalty database or the details of the customer as well. So all in all, if you see, you are moving closer to your business domain with such a kind of architecture at play. Now, talking about where you would see such message-driven architectures at place, when you have communication between services, when you want modules in modular monoliths communicating with each other, you can investigate into message-driven architecture. In real life, you would see such architectures at play in industrial automation, healthcare systems, banking and finance. Anywhere you want to have high throughput, high performance scenarios, mission critical systems, messaging architecture can vitally help there. And if you are thinking about messaging architecture, these are some scenarios where you shouldn't be using them. CRUD applications, when you need request response, or even real-time application. Now, revisiting the fallacies of distributed computing, what is the verdict? How does messaging fare? So, network is reliable. We embrace failure by design by introducing durable storage, retries, and DLQs. With the latency, we have introduced async processing, and we have decoupled time. There's nothing called an instant processing. It is all eventually consistent data. We are tackling bandwidth by achieving some load leveling, because backend systems could process at a normal rate while the client UI alone is scaled. So there's load leveling happening. The network is secure because all the message brokers, they take care of TLS encryption of in-flight services. And with fine-grained services, the attack surface is also reduced. With the topology that doesn't change, we saw that we can evolve with minimal disruption. We can take entire consumers down for maintaining and servicing, and that doesn't impact the entire system at all. We can have different teams working on different parts of the distributed system, and they all can work independently and have team autonomy. We can scale just the necessary services and deal with the spikes. For example, you could just scale the client UI alone to have multiple instances for the user-facing fend, and then the backend services could be just one instant and keep processing data at a normal pace, achieving load leveling. And we have an inherently polyglot-friendly architecture in place because the underlying protocols like AMQP and MQTT, they are language agnostic and enables communication across different platforms. It doesn't solve all the problems. What messaging helps you is confront the fallacies early on. And these fallacies, as they are, you are forced to ask yourself those questions early on to mitigate the risks. So that is it from me today. That is the QR code to my resources and my resource link as well. And if you want to reach out to me, feel free to reach out to me at Purnima Nair. Thank you. And thank you once again for having me as a speaker.